Hello, my name is Muhammad Tariq. I'll be presenting to you today a tutorial about how to fit non-identifiable models and poorly identifiable models using Bayesian inference. This video will be a part of a whole video series about Bayesian inference in Pumas. Not just the how to do Bayesian inference, but also why you would need to do Bayesian inference sometimes, and all the things that you can do with Bayesian inference in Pumas. Focusing a lot on the workflow, on the use cases in pharmacometrics, and not so much necessarily on the math of Bayesian inference, which I'm going to assume that people here are somewhat familiar with already. So this tutorial is actually public tutorial. So we have it here. If you go to Pumas tutorials, which is this website here. So if you go onto this tutorials.pumas.ai, you'll find a whole list of tutorials available to you, and this is one of them today. So this is the fitting non-identifiable models tutorial. So if you click on that, you'll see this. I'm going to basically walk through it, explain the main key points or the key points there, and also hopefully walk through the code here and maybe interactively show you a couple of things. So I have an interactive version of the tutorial here, and I have the pre-rendered version of the same tutorial on this website. Okay, so let's get started. So a lot of times when Bayesian inference is presented to you or to a practitioner, the appeal perhaps or the argument tends to be very theoretical, that, oh, we want to get the full posterior distribution instead of just the maximum likelihood estimate. And there's often this contrast between the two. Should we do maximum likelihood or should we do full Bayesian inference? And today I'm hoping to show an example where we can kind of motivate this or say the same thing but in more practical terms with an example, and show you exactly what happens when you try to use more classical maximum likelihood estimation methods to fit a model that could be poorly identifiable, and we'll come to what that means in a second. And so the idea of Bayesian inference and getting the full posterior basically can protect you when trying to analyze or to fit your data to a model that you suspect may not be identifiable. So what exactly is this whole identifiability thing? So model identifiability in layman terms means that you can almost reverse engineer the model. Like if you observe some data, if you look at the output of the model and actually observe it with experiments, you can recover the data generating parameters, the parameters that are most likely to have generated this data that you're seeing. And as you see more and more and more data, you can kind of be more and more confident in your predictions, in your estimation of the parameter that you think or is most likely to have generated the data. So notice I said estimate and most likely, hence maximum likelihood estimation. And so the idea is that you want to be able to get those parameters, and a model is identifiable in theory, or structurally identifiable as it's often called, if assuming we have unlimited data. If we observe infinite amounts of data, we should be able to basically precisely find out which parameters or which parameter values generated these data. Now, when is this not the case? So this is typically not the case when your model is over-parameterized. And so there could be multiple parameter combinations, all of which basically give you the same prediction. And so even if you observe an infinite amount of data, there's still this natural kind of redundancy in your model that you can always change some parameters, maybe increase one, decrease one, and get the exact same model or get the exact same prediction. So that's often a case. Another case is sometimes you have maybe not a whole continuum of values. So the first case is when you have over-parameterization, you often have a whole continuum of values, like maybe theta from 0 to 1, all of which give you the same prediction. But you could also have discrete but disconnected values. So maybe theta equals -1 and theta equals 1 give you the same model prediction. And this could happen, for example, if you inappropriately use the absolute function or the absolute value function in a model where the input is unconstrained, can go from minus infinity to infinity. And so you're creating a symmetry where any positive or negative input to the absolute value function will give you the same output and thereby giving you the same prediction at the end. And so if this parameter, if this input is not used elsewhere in your model, and this is the only place it is used, then you have a problem. You have this kind of symmetry. And so if theta equals 1 perfectly describes your data, then theta equals minus 1 will also equally perfectly describe your data, because they both give the same output of the absolute value function. But this kind of symmetry or this kind of non-identifiability can often be resolved if you have a preference of one over the other. If you know that theta should be positive, and so perhaps you just forgot to add a constraint on theta, but sometimes it's not very straightforward. To figure out how to kind of break the ties between those parameter values. And making your model identifiable is all about breaking ties. So if you have multiple parameter sets, all of which can give you roughly the same model or exactly the same model, then that's usually a bad place to be in because that means you cannot uniquely identify your model parameters. But to try and break ties, that's basically that's identical to saying that I'm trying to make my model more and more identifiable. And this could be either by simplifying the model so that I don't have multiple parameter values, all of which give me the same output. That shows maybe that my model is overcomplicated. Or it could be by observing more data. So maybe if I can observe some more responses, I can make some parameters identifiable. So that's kind of the idea. So that's structural identifiability. Now, there's another type of identifiability, which is called practical identifiability. And the idea is that even if your model is in theory structurally identifiable, and by that what I mean is, so there's a nice table here that actually summarizes all the different types of structural and practical identifiability, and there's the global and there's the local version of that. So I encourage you to take a look at that. But basically the practical identifiability has something to do with where your experiment design, so where your observations are. If perhaps, for example, let's give an example. If all the observations happen early on, before the drug is fully absorbed into the blood, it will be very difficult for us to estimate the clearance parameters in your model. So that's a very practical example of practical non-identifiability issues. And so normally you would need to have observations across kind of the whole duration of the drug absorption and the clearance period so that you can estimate both the absorption and the clearance parameters. So even if in theory, assuming you have infinite amounts of data, your model could be identifiable, but because your experiment design was so bad that you focus only on one region or one part of your dynamics and not the other parts, you still may not be able to estimate some of the other parameters. And so this is often called practical non-identifiability. And you can think of this as basically a model data mismatch. So you're modeling something or more things than you're observing, or basically you're modeling along a longer kind of duration and you're observing only in very small duration or a very short window. And so your model and data are not really perfectly matched. And so in that case, getting more observations would help, or designing your experiments in a better way would also help, so that you can hopefully get more information. And this whole topic of optimal design of experiments is very interesting, but it's not the topic of today. But there's a whole methodology to how you could basically optimize your design so that you can maximize, not just make these parameters identifiable, but also maximize the precision by which you could identify those parameters. Because making more observations is not always, more observations is generally a good thing, but it could be better if you could space them out in certain ways and design your experiment so that you make the most out of every observation that you take, or out of every sample that you take. But that's not the topic of today. Today, the topic is about Bayesian inference. And so I'm going to intentionally assume that your model is of this class, that is non-identifiable models. And I'm going to assume that it's local non-identifiable, or at least locally non-identifiable. So what that means is, if I assume that I know the true parameters theta, then I can, let's say I simulate from this parameter. So I have my parameter theta, I simulate from it, I get a whole bunch of simulations. Now, if I try to identify or estimate the parameter theta, there could be multiple kind of changes in theta, local changes. So I can increase maybe theta 1 and decrease theta 2, or increase theta 2 and decrease theta 4, and basically get roughly the same model at the end. And so all of these different values, they're all very close and local, basically around theta, all of which give you the same predictions or give you the same log likelihood. So we will, again, talk more about that in a second. So the term poor identifiability. So I mentioned that some models can be identifiable, some models can be non-identifiable. So what does that mean when it comes to computation? Because when we compute things, so I said that, let's say 2 parameter values give you the same predictions. That means your model is not identifiable, because I can observe a lot of data and still not be able to figure out which of those 2 parameter values is the true set of parameter values that we use to generate the data. But what if they don't give you the exact same prediction? What if they're very, very close predictions numerically? So the predictions are approximately equal. I can change the parameters significantly and get very little change in the output of the model. When doing computation, it's sometimes difficult to distinguish between these 2 cases, the true non-identifiability versus the numerical kind of or approximate non-identifiability, where the predictions are approximately equal for different parameter values. And so kind of to be more general, we're going to use the term poorly identifiable to refer to this case of a model being perhaps not exactly non-identifiable, but maybe given the design that we have, it's hard to tell exactly which parameter values produced the output or gave us or are likely to have generated this data, right? Or likely to be the true parameter values that actually generated this data. So if we can't really tell if multiple parameter values have approximately the same log likelihood, then that's what we're going to call poorly identifiable. And this covers the case of true non-identifiability when they're exactly equal. But again, with arithmetic, with floating point arithmetic, doing computations on the computer, sometimes it's difficult to distinguish between these 2 cases. So sometimes we'll use this more general term, poorly identifiable. Okay, so let's go ahead and see an example to kind of bring all of this home and try to make sense of it. So at the beginning, we're going to need to load Pumas with this, using Pumas. In this case, I'm using a very familiar model, hopefully, which is a 2-compartment model. And it's only a single subject model, so I'm not considering population models yet, or hierarchical modeling yet. But this is still very relevant even when discussing hierarchical models for a reason I'm going to mention in a second. But basically, this is just a 2-compartment model with a depot where the drug goes in bolus dose, and then a central compartment and a peripheral compartment. And we only observe central divided by VC. So we observe the concentration. And here I have a proportional error model. I'm using this absolute value function because sometimes CP can be exactly 0, but numerically it could be slightly negative because of floating point errors. And so just to protect against floating point errors, I'm using this absolute value function, guaranteeing that this is always non-negative, basically, even if the floating point error makes it minus 10 to the power of 16 or something like that. And then I'm adding a small threshold to make sure that the sigma is never 0, even when CP is 0, because initially, for example, the concentration of the drug in central is assumed to be 0, and so just to make sure that the standard deviation is never 0, which can cause numerical problems, I'm adding a small value here to the standard deviation. So that's, again, a very familiar model. It's a 2-compartment model with a proportional error model, right? And we only have fixed effects. We don't have any individual parameters or omegas in here, so it's a very, very simple model. Okay, and that's how you would write it in Pumas. Now, I'm going to assume some familiarity with Pumas syntax. If you're not familiar, there is a wealth of other material and videos that you could refer to in order to learn more about how to write models using Pumas. So some familiarity will be assumed in this tutorial. All right, so this is again a subject-specific model. So there's a nice kind of comment here about what, the relevance of this kind of model, even when doing a population model. Because if your subject model is not identifiable, that means your population model is pretty much guaranteed to not be identifiable. So it's always good to analyze first your individual model. Make sure that perhaps given a lot of data or enough data or maybe representative data given your experiment design, that you can actually estimate the parameters for each subject individually first. And the reason why this is relevant is that even when fitting a population model, there's actually a step in the fitting when using maximum likelihood estimation to compute these so-called empirical Bayes estimates. And the empirical Bayes estimates they can be very unstable if your model is not identifiable. So you can get these kind of poor estimates of the empirical Bayes estimates or poor empirical Bayes estimates if your subject model is not identifiable. And that can cause all sorts of numerical issues as well. And so you could end up with having identifiability issues at the subject level can trigger non-identifiability issues at the population level, but can also trigger numerical errors. So your model could just break down due to numerical errors, or your fit could break down due to some numerical errors. And so it's always good to look at the individual model first. And so that's what we're focusing on in this tutorial. And again, we go into a bit more details here in this note. But moving on, so we're going to define some parameters here. These are assumed to be the data generating parameters. So that's our theta vector, and this is our standard deviation in the proportional error model. Okay. Next, we define what we call a subject in Pumas. A subject in Pumas is used for multiple purposes. In this particular case, we're using it for simulation. First, because we want to generate a synthetic data or a synthetic subject. But we're also using it to do something, or compute something called the Fisher information matrix, which we'll cover next. But basically, this is, I'm going to call this a skeleton subject. And the reason is that it doesn't really have any observations, as you see here. It's dv equals nothing. And what that means is that we acknowledge that there is a variable called dv in the model. So we want to make this subject kind of compatible with our model. So our model assumes that the derived variable dv is the observed quantity here. And we acknowledge that this subject has an observation variable dv, but we don't really have a value for it yet, so we give it a value of nothing. Now we're going to use that skeleton to then simulate values here. But this is how you kind of write a skeleton subject in Pumas. We still specify time points, and those will by default be the observation times, or the times where the simulation will be done. So we're going to be generating one observation for each time point. And you see here we're doing kind of relatively dense sampling, so that's like 61 observations for this subject. And the reason is we're trying to get an idea of how identifiable are the parameters, assuming we have sufficient data, assuming we have good amount of data, right? A realistic, perhaps unrealistic amount of data, but not way too much data, just a good amount of data. And again, you can really experiment with this design, and the idea is like if somebody came to you and asked you, when should we measure or take samples for this patient, that would be such that you can kind of maximize the information or learn as much as possible about the parameters of interest or make certain parameters identifiable. This is kind of what you would be playing with and adjusting until you get a good design. So this is basically part of your experiment design, which sample times to use. So we're going to specify this kind of somewhat dense sampling here. Next, we're going to specify a dose, which is a bolus dose at time t equals 0, given in compartment 1, which is the depot compartment. And it's going to be or have a value of 3000. And this is a somewhat arbitrary value here, just to make the example work. Okay, so next, what I want to do is actually show you a workflow for how you could detect non-identifiability or poor identifiability. And so what we're going to do is use this idea of a Fisher information matrix. Now, for more about the Fisher information matrix, there is actually an entire tutorial. If I go back here, It's Introduction to Optimal Design, which goes through exactly what the Fisher information matrix is and what it means and how to calculate it and stuff like that. And so I'm going to assume some familiarity with that, but please go back and read this if you're not familiar with what the Fisher information matrix is. But going back to this tutorial here, the goal here is to get an estimate of the Fisher information matrix at theta being the parameter values that we chose here. So, or the theta and sigma that we chose here. And so the way to do that is using this optimal design package. We're going to use this syntax just to wrap the time points of the skeleton subject. So these time points are basically the 0 to 30 with intervals of 0.5. And then we're going to pass this on to the FIM function or FIM function from optimal design. And this is basically the syntax for this. So we get here a 6x6 matrix because we have 6 parameters. It's symmetric and it's positive semi-definite or positive definite. We'll see. It's positive definite if it's positive definite, then your model is basically that's already a proof. You can think of this as a certificate of local identifiability. If this matrix is positive definite, then we say that your model is locally identifiable given your experiment design that we used, given the sample times that we chose and the dose that we chose and the covariates of the subject and so on. So all of these are part of your experiment design. If it's not positive definite, that's not, meaning if it's singular, so if it has some 0 eigenvalues, that's not really a proof of non-identifiability. So we'll see how, like in this case, it's actually very close to being singular. And even though that's not quite a proof of non-identifiability, you can actually use it to prove non-identifiability as one step of the way. So hopefully by the end of this tutorial, you will be able to kind of detect when your model is locally non-identifiable or at least poorly identifiable given your experiment design. Okay, so that's our Fisher information matrix. Now let's go ahead and get the eigenvalues. So we can do this and perhaps it's nice now to switch to the more interactive version of this tutorial. So over here I can basically rerun this. And let me show you again. This is the matrix here, all right. So this is a rendered version of that tutorial, and that's the interactive version. So let's stick to the interactive version, unless we need to look at the pretty printing of these values here. But yeah, so that's again, that's our Fisher information matrix. So what I'm doing here is just taking the eigenvalue decomposition of this matrix, and this actually gives us an object that's so if I do this will give us an object that's an eigenvalue decomposition object, and I can get the values of this eigenvalue factorization, or I can get the eigenvectors as well. So the eigenvectors, each column will be an eigenvector corresponding to each value in the eigenvalues, right? And so what we can see here immediately is, first of all, the eigenvalues are sorted. Second, the smallest or the first value is actually very close to 0. And there's the condition number is large. So what is the condition number? It's the ratio of the largest eigenvalue to the smallest eigenvalue. So if I divide this number here by this number, I can get a pretty large condition number. So those are all bad signs, or at least the fact that the condition number is large is a bad sign. The fact that the smallest eigenvalue is close to 0 is a bad sign. But what does that really mean? All right, it means that it's possible that your model is not identifiable. And to actually prove that, and again, I said that it's not really a proof. If the Fisher information matrix is singular, it's not a proof that your model is not identifiable. However, you can use it as a step to prove that. And the reason it's not a proof is that there are models with singular Fisher information matrices that are perfectly identifiable. So you could actually write down models. Some of them are slightly kind of artificial, or they're designed as a counterexample, and so they're not very commonly found, probably. And so it's possible to write those models such that they have both a singular Fisher information matrix, meaning the smallest eigenvalue is exactly 0 in exact arithmetic and approximately 0 in floating point arithmetic, but the model is actually identifiable, and so you could, every parameter value gives you a unique prediction, and so your model is perfectly identifiable. And so you could design such models or write down such models, and that's why, just to be on the safe side, you cannot conclude, or to be correct, really, you cannot conclude that a model is not identifiable just because the eigenvalues are close to 0. However, we can use this as a way to, or a step to prove non-identifiability. And here I go into kind of this same explanation that being non-singular is not always a must. Okay, so how do we actually prove non-identifiability, right? Like, let's say we have a model. How do we go about trying to prove that it's not identifiable? If the Fisher information matrix is singular or is close to singular, that means we kind of failed to prove it's identifiable. It could still be identifiable, we don't know, but we couldn't prove it. But can we actually prove the opposite? If we can prove the opposite, then that's also very good to know, right? So either proving identifiability or proving non-identifiability. You should do one of those two, and then the other follows. So since here again the Fisher information matrix has a minimum eigenvalue of that's a value very close to 0, we could try to use this as kind of a step of the way to prove non-identifiability. So what we're going to do is actually follow this procedure here, and so let's go through it step by step, and perhaps we can do that in this form. So first, what we're going to do is assume certain parameter values. So those are theta 0. So let's assume some parameter values are the true parameter values. They're the ones used to generate the data. Next, what we're going to do is define some criteria by which we can change the parameters theta 0, or theta to be around theta 0, and create a candidate set. So create a set of parameter values. So recall, what do we mean by non-identifiability again? It's when or how can you show non-identifiability? If multiple parameters give you the exact same prediction or log likelihood given a lot of data, then that's a proof of non-identifiability. You can show that your model is at least practically non-identifiable given your data by showing that the log likelihood is basically not very sensitive to the parameter choices. I can change the parameters, gives me the same log likelihood, right? And so, or again, that's let's say poor identifiability. Let's use that term just to be perhaps more generic about the case where models can be approximately non-identifiable. Okay, so we're going to define a criteria. We'll come to what that criteria is, and this criteria will use the eigenvectors of the Fisher information matrix, right? So that's where it's actually useful to define this criteria. Now, next, we're going to simulate a synthetic data. So we want to simulate a subject, some observations given our skeleton subject. Then we will evaluate the log likelihood at theta, or at all the parameter values in this candidate set. So this candidate set is a set of parameter values that we have decided to test or include in this theta C, given some criteria for choosing those values. And then for all of these theta values, all these parameter values in this candidate set, we will evaluate the log likelihood for them. Next, we will try to estimate or evaluate the sensitivity of the log likelihood, or do some sort of sensitivity analysis of the log likelihood to changes within theta C. What that means is, what happens if I go from one value of, or one set of values for the parameters to another set of values in the parameters, or for the parameters in theta C, right? Moving around in theta C, how sensitive is the log likelihood to those changes? So the way we're going to construct theta C is using this very simple recipe here. So let's kind of deconstruct this a little bit. So we're going to start from theta 0, and then we're going to basically move theta 0 along the direction D, move theta 0 along the direction D by a step alpha. So alpha here is a scalar, theta 0 is a vector. that's equal to the length of, or the length of that vector is the number of parameters in your model. And D is another vector whose length is equal to the number of parameters in your model. And alpha is just a scalar that's going from minus epsilon to plus epsilon for some small step size epsilon. So I'm going to define a window from minus epsilon to plus epsilon, and then I'll pick a whole bunch of alpha values in this window, and then move theta 0 along the direction D by a step size alpha for different alpha values. I can pick alpha equals minus epsilon plus a small amount, minus epsilon plus slightly bigger amount, all the way until epsilon, right? So I could have a kind of a discrete choice. Now, next, what I want to do is to get the sensitivity analysis, or do sensitivity analysis. And so to basically compute a metric that's a measure of sensitivity of the log likelihood. This is one such metric, so we can do this. We can get the log likelihood at the new parameter theta 0 plus alpha times D, and then subtract from that the log likelihood at theta 0. So this gives us the change on the log likelihood. Then we can divide by the step size, right? So this is kind of the finite difference approximation of the derivative. And then we can take the square of that. And so the idea is that this term is always going to be positive, right? And it could be a small positive number if, for example, L is not changing. So if you think of L as, if L is not very sensitive, if L doesn't change at all, then the numerator is 0, and the denominator is a scalar. That's it's not 0. And so then you get basically 0 sensitivity, which makes sense. Now, if L is changing by a small amount, it's much smaller than alpha, because naturally, if alpha is small, then the change in the log likelihood will also be small. So what matters is really the relative change between the size of alpha, how big of a step have we taken, and the size of the change in the log likelihood as a result of taking that step. And so if the change amount is much smaller than the step size that we're taking, that's a sign of non-sensitivity, basically, or your log likelihood is not very sensitive. And when your log likelihood is not very sensitive, on average, across theta c, that's basically proof of non-identifiability, or at least poor identifiability, right? It means that I can change my parameter values at least locally, so that's a local change here, right? I can change my parameter values locally and get likelihood values that are very, very similar, right? And that tells me that my model is not very sensitive, at least to local changes in the parameter values. It might also not be sensitive to bigger changes. Maybe if I add a larger value to theta, it could also give me the same log likelihood, but that's not what we're testing for here. We're just testing for local non-identifiability using this method. So let's go ahead and try to follow this recipe. I'm going to go back to the interactive mode. And so we'll see here that we're just loading this random package, or a package called random, and we're using the default random number generator, which is actually a pseudo random number generator, to kind of set the seed for the simulation. And if you're curious to understand more about how to make your simulations reproducible and set the seed, we actually have an excellent tutorial on that as well. So let me go back here for a second and try to find this tutorial for you. So there you go. So this reproducibility when doing simulations. So if you click on this, you see that it's written by Jose Stropoli, who spent a lot of time trying to make this very easy to understand and easy to follow and make sense of. So please go ahead and read this to kind of make sense of how to make simulations reproducible in Pumas. But I'm going to use this nice feature of Pumas and go ahead with my example. Okay, so here I'm using a random number generator and then fixing the seed just for reproducibility. And then I'm defining a single subject population. So this here is the syntax for defining a subject. For simulating, so simobs. So let's break this down a bit, right? So let's break this down a bit. Okay, so this here will simulate or generate something called a simulated observations struct or an object, and we can then convert this to a subject. So if I call the subject constructor around this, so that's another way to use the subject constructor right? We've seen how to use a subject constructor to define a skeleton subject before, right? The same constructor here. Now we can pass different inputs to it and get a different behavior, and that's what this whole multiple dispatch thing of Julia is all about. So you pass in different types of inputs, you get different behaviors for the same function. And so this here, we're actually using it just to convert the output of SimOps to a regular subject, which we can use for fits and simulations and so on. This is a technicality, but it's an important one that we need to be aware of. Next, we can define a vector of things, any kind of things, using this syntax that's opening square brackets and closing square brackets. And so now we basically have a vector of subjects, which is what we call in Pumas a population. And so that's what this one line of code here does. It first simulates a subject given the skeleton that we have, then it converts the output of SimOps to a regular subject, and then it creates a single subject population with the square bracket syntax. Okay, so hopefully that is clear. So let me redefine this. And next, what I'm going to do is use the log likelihood function to get the log likelihood of this synthetic population. So let's go back to our multi-step procedure for detecting non-identifiability. So we need to define parameter values theta 0. So we're going to assume that this is basically params. So assuming theta 0 is the parameter values that we define, which just to remember, let's add them here. So these are the values of theta 0, right? So these are all the parameters that we have. Next, the next step is to define a criteria. We'll come to what that criteria is in a second. And then we want to simulate synthetic data. So we did that. We simulated synthetic data, which is this pop or single subject population that we have. And now we want to evaluate the log likelihood for all theta within theta c. And so let's walk through that step one step at a time. So first, I'm going to evaluate the log likelihood at the theta 0, which is params, and I'm using the log likelihood function, which takes in the model, the data, the parameter values as arguments, and takes in an algorithm for defining the log likelihood. Now, because this is a single subject model with no random effects, I'm going to use this naive pooled struct here, and these four arguments basically together, when you pass them to log likelihood, it will give you the log likelihood of the parameter values given your data and your model using whatever algorithm you chose here. In this case, the log likelihood is shown below. And I'm going to call this LL0, which is the log likelihood of parameters theta 0. Okay, now let's come to our vector D. So I said that we have to move our parameters theta 0 across or along a direction D. Now, which direction should we pick? Given our eigenvalue decomposition that we have, which is E here, so this was our eigenvalue decomposition from earlier, the first eigenvalue is close to 0. What that means is that it's possible, it's not confirmed yet, it's possible that if we move theta 0 along the first direction here, the first eigenvector, which is this column here, right? If we move theta 0 along this direction, that the log likelihood might not be very sensitive to the changes in that direction. And again, that's not a definitive proof yet. We're going to do the actual test because we don't know for sure yet. But that's what this small eigenvalue here tells us. And there's a bit of math that you can show to prove that. Basically using the second order Taylor series expansion of your log likelihood around theta 0, you can show that the direction along which, or the eigenvector that's corresponding to the smallest eigenvalue, is basically the one with the least sensitivity, where the log likelihood, if indeed a quadratic approximation is a good approximation of your function, then that direction gives you the direction of least sensitivity, where I can move along that direction and at least locally, and the log likelihood will not change that much. And so mathematically, this is actually correct. And you can, again, demonstrate that. But we don't always know if a quadratic approximation is a good approximation, because your model could have some non-smoothness in it and so on. Or it could be like piecewise linear log likelihood functions. So we don't always know that this quadratic approximation is a good approximation of your model, and therefore it's not definitive yet. But what we can do is basically take this as a candidate direction D and use it to generate our candidate set theta C, or uppercase theta C. And so that's our choice of D, basically, in this test, which is the eigenvector corresponding to the smallest eigenvalue. Now, to get the first column of a matrix in Julia, we use this square bracket syntax with a colon to get all of the rows in the first, so all of the rows and then the first column here. So this here gives us exactly these numbers here, right? Which is the first eigenvector corresponding to the first eigenvalue, which has a value close to 0. This is our direction D that we're going to use as part of this test for non-identifiability. But notice one thing is that the last number in this direction D is very close to 0, at least compared to the other numbers. Now this is a normalized vector, by the way, so this is a vector whose norm is 1. Now what that means is if I call the norm function on this direction D, it's going to be very close to 1. The norm is also just D transpose times D, so that's very close to 1, where this here just means transpose, or the adjoint vector of D. So this is a normalized vector, and so this value here is very, very small, basically, and we can safely ignore it. So when moving theta 0, along the direction D with a step alpha, we can safely just ignore the sigma, which is the last parameter. All right, so what we're going to do is define a function here, move theta. This function takes an input alpha, and it moves the value or the parameters by a step alpha along the direction d1 to n-1. So I'm just removing the last value, which is close to 0. There's no point adding it to sigma here. And the order of values in D, by the way, is basically the same order of the parameters in the model. So if we go back to the model, you'll see that we have theta first, which is 5 values, and then sigma, which is 1 value. And so this same order is what we should be interpreting this D vector as. And so we're adding the first 5 numbers here to theta, and then the last number is close to 0, so we're just ignoring it. So that's what this function here does. It just unpacks params. So this is a way to unpack a name tuple. So params is just a name tuple. So I can probably show how to do this. So this is just a name tuple here. Now if I do this, this basically unpacks params to give me separate variable theta and a separate variable sigma as well, right? So that's just an unpacking syntax here to give me 2 variables, theta and sigma, and then I'm taking theta and I'm adding to it alpha times d until, or the first 5 numbers of d, and then I'm leaving sigma unchanged, and I'm creating a new name tuple here. All right, so let's just hypothetically, let's assume that alpha equals 0.01, and I am doing this operation here, and I already kind of unpacked params to give me theta and sigma. When you do this operation, you get another name tuple of theta and sigma, but with slightly changed values of theta, right? So you'll see that the values here are slightly different, right? So that's what this is doing. It's just a function that takes in different alpha values and returns the new parameter values. Now next, I'm defining a whole bunch of step sizes alpha from minus epsilon to plus epsilon. So epsilon here is just 1 times, or 10 to the power of minus 3. And I'm taking a whole bunch of, well, actually that's not epsilon, but epsilon is 10 times that. So what I'm doing is I'm taking 1 to 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I multiply each one by 10 to the power of minus 3, and I do the negative of that and then the positive version of that, and I concatenate everything. So if I evaluate this, it basically gives me a whole bunch of alpha values or step size values that I can use for testing this sensitivity or doing the sensitivity analysis. So these are all the step sizes alpha that I'm going to use. Now next I will call this function move theta on all the values of alpha that I have selected, and I do this with the broadcasting syntax here to call a function on each value in a vector, and it gives me a vector of name tuples where the vectors, the values are slightly different, as you can see here. The sigma is the same because we chose to ignore that dimension, at least when moving along D. Now, to get the log likelihood of all these different, so these are all different parameter values that we can see here. And the idea is we want to see is going from one value to the next, or going from theta 0 to each of those values, actually, does that cause a significant change in the log likelihood, or how sensitive is the log likelihood to changing from theta 0 to one of those parameter values, which corresponds to a specific choice of alpha or a step size alpha. And the way we compute the log likelihoods at all these different parameter values is using this syntax here for the map function. And so you can call the function map in Julia with this syntax, which we call the do block syntax sometimes, or the map do syntax. And basically you can read this as just a for loop, essentially. So we're iterating over all the values of new params, and for each value of new params we are assigning this value, so one of those name tuples here, to the variable p, and then we are computing the log likelihood with the same model, the same data, but with a different parameter value p. So this is like a for loop that basically returns a vector of all the log likelihoods from all the iterations of the loop, if you think about it like that. So what we get here again is log likelihood values that are all very close to each other, but it's hard to tell whether or not this means that they're sensitive or not, because the alpha values are also close to each other. So now it's time to actually do the sensitivity analysis. And so the way we do it is using the formula that we saw earlier, which is this formula here, and we do that for every choice of alpha and then take the average value across all the alpha values. And so we do it here by first, so let's break this down. So LLS, or the log likelihoods vector, this is a vector. This here is a scalar, so we're doing an element-wise subtraction here to get the difference between each element in log likelihoods, or LLS, and between the log likelihood at theta 0. And then we divide, again, element-wise, so this dot and then division is basically element-wise division, and what we're doing here is just getting this ratio, right? And then we take, again, element-wise the square, or the kind of the square of the absolute value, which is just this. This is a function that basically returns abs of x squared, or just x squared. And it's just does the squaring. We could have also done it slightly differently. So we could have just taken the dot and then caret and then square, and so that's again element-wise taking to the power of 2, or squaring this number, and this will give us so maybe we should evaluate this line separately. This will give us another vector, actually. That's the vector of these terms here, so the ratio squared between the change in log likelihood divided by the change in theta, or the step size. And next, what we can do is get the mean value of this, and what we see here is that it's actually indeed pretty close to 0, right? So it's not exactly 0. Again, it's hard to be definitive. It's hard to know exactly when a model is truly non-identifiable with this test, but we can at least get signs of poor identifiability. So this is a pretty good sign of poor identifiability, and actually to kind of get an appreciation for whether or not this is a small number, let's do the same procedure, but this time for a completely random direction D2. And again, in this case, we are ignoring the last number of D, of D2, And what we're doing is just taking the first 5 numbers of D2 and adding it again to theta. So this is the same procedure, just with a different vector D2 that's also normalized. So we first normalize it. So just get a random vector, normalize it, do the same procedure, and then get the mean value. And you'll see that the mean value in this case is significantly higher, right? It's 1,600 something. Compare this to this sensitivity analysis. And so with this, we can pretty much conclude that our model is not very sensitive in this direction, and that there could be some, or there's a very strong sign of poor identifiability. Now, have we proven non-identifiability? Probably not. So in that case, it was false advertisement. But we at least showed that there is or there seems to be some significant identifiability issues, which numerically speaking is basically equivalent to saying your model is non-identifiable, because at least in floating point terms, your model is very close to being non-identifiable. Okay, so this is a procedure that hopefully you can use with your model. We intend to hopefully make it slightly more refined in the future, but this is something you can do now with your current Pumas model and figure out whether or not your model is or has identifiability issues right now. And with your current experiment design. Now, one thing that we could do is, well, let's try different designs and see if we still have these identifiability issues. And there's a clever way to do this, and we can cover those in future tutorials. But for now, I'm hoping to have shown you kind of the way of how you can test for either identifiability by showing that the smallest eigenvalue is far from 0. So that means your Fisher information matrix is not singular, and that's a proof of identifiability, right? Or by proving the opposite, which if your matrix is very close to being singular, you can go ahead and take the eigenvectors corresponding to the smallest eigenvalue and then use it to construct this test here and do the sensitivity analysis. And that's basically the second way which you can use to prove perhaps or attempt to prove non-identifiability or poor identifiability. And if you can show this lack of sensitivity, then what you should do is actually look at your vector D closely. So look at this direction here. So let's take a look at this. It's actually, you'll notice that the first parameter, the third, and the fifth and sixth, they're very small values. And so really the only significant values are the second and the fourth, right? And so what that means is when we're moving along D, what we're doing is we're adding or changing theta 2 and theta 4 in opposite directions. And so we can either increase one and decrease the other or vice versa. Now those parameters correspond to VC and VP. And so that's where this fuzziness in the model is, where I can increase VC and decrease VP or vice versa and get roughly the same model at the end or the same log likelihood. And that's what we can actually read from this vector D. And so with this information, now I can go back to my model and see, all right, what happens if I fix one of those two? And that can guide or can give you options as to how you can fix these identifiability issues as well. So looking at the vector D, if indeed your model turns out to be very insensitive along this direction, then this is a very useful diagnostic to look at and actually help you change your model and figure out which variables seem to be interacting in such a way that it would give you the same log likelihood at the end. So if I change them all at the same time, you get roughly the same model at the end, or at least all these models explain your data equally well. So with this procedure, again, hopefully you know how to now detect identifiability issues. But let's say we know our model has poor identifiability issues, but it is a good model. We want to use that model. Maybe it's a QSP model or a PBPK model or something that has a lot of parameters. We don't quite want to fix any of them. We want to investigate kind of the extent to which we can change some of these parameters and still get good predictions or still explain our data. And in that sense, basically, we don't care that the model is poorly identifiable. We still want to fit it. right? We think that the model is meaningful. And that's actually an important distinction, that just because a model is not identifiable does not mean that it's useless. It's actually sometimes the opposite, in that if your model is more kind of biological, more accurate, tries to model a lot of things about what's happening inside the body, these kinds of models tend to be more non-identifiable. And so that limits certain things you can do, like you cannot identify, obviously, the true parameter values from your data, but maybe that's not what you're trying to do. Maybe what you're trying to do is just get an idea about how widely dispersed your parameter values are in the posterior. So how much can I change these parameter values and still get a good model, and maybe I can still get some useful insights from that, right? So going about fitting poorly identifiable models is still kind of a valid cause or goal, even if your model is not perfectly identifiable, given your data or given your experiment design. Okay, so how do we actually go about fitting those non-identifiable models or poorly identifiable models? So in this part of the tutorial, I'm hoping to kind of walk you through all the options that people normally use, or the main option really that people use, and hopefully convince you at the end that with these kinds of models, using kind of more traditional maximum likelihood estimation methods, whether it's Laplace or FOCE, can actually cause some issues. And in this particular case, we don't have random effects. I'm going to use just regular kind of naive pooled, which maximizes the conditional log likelihood, or minimizes the negative of that. But kind of the same insights can be extended to the case when we have random effects and when we're actually marginalizing the random effects and getting the marginal likelihood. So what exactly is the issues, or what exactly are the issues with using maximum likelihood estimation for these methods? Well, the main issues, I would say, are that you could potentially get arbitrary outputs or arbitrary estimates of the parameters, because the parameters are kind of not uniquely identifiable, and therefore any values, or if the algorithm returns you any set of values that correctly fit the data, then that's the algorithm doing its job. It's giving you something that fits the data. But the problem is that this does not necessarily represent the entire diversity of possible values that could fit the data. And so if you actually draw some insights or try to draw conclusions from the values that you get, you might be making incorrect conclusions as a result. And so in this section here, what I'm going to show you is basically how the maximum likelihood estimate can be very sensitive to where, or how you initialize the optimization, to how much noise is in your data. So even if your mean is the same, but your sigma is not, which again, like the whole point is to show you things that may seem arbitrary, or they should not really affect too much the parameter estimates, but apparently if you change just the noise level, you can get completely different estimates for the other parameters as well. And that's with dense sampling, so that's with sufficient data that we have quite a good amount of data for the subject. And then one thing I don't really show here, but it's good to kind of ponder upon, is that your maximum likelihood estimate that you get out of your algorithm is actually going to depend also on the implementation details of your optimization algorithm. So a lot of optimization or fitting software, including Pumas, we use this so-called BFGS algorithm for optimization. And this requires the construction of a matrix that's approximating the inverse Hessian of the objective function. And again, there are quite a few assumptions that go into that. And often you'll find that some algorithms work better than others, but if you try different optimization algorithms, you might end up with very different estimates, basically, with these kinds of models. But the idea here that I'm trying to emphasize is that the fits that we get are basically very sensitive to a lot of factors that should not really affect the solution, should not really affect your conclusion in a clinical trial. And so in some ways, you are putting yourself at risk when you use these methods or maximum likelihood estimation methods with these poorly identifiable models in that you could be subject to one of those issues here, right? And so let's take an example. So here I'm showing an example where we basically initialize the parameters. So maybe I can switch to the interactive mode for that. So the true parameter values from which we simulated the data are basically shown here. And here, so I basically initialize it from the same value, right? So we should assume that we can get something close. So the initial values here that we're using for the fit are basically the same as the true data generating values. So what happens when we fit? We get something. So let's take a look at what we actually get. So these are the parameter estimates that we got, which again, if you compare them to the true parameter estimates, so if you compare these values here to these values, they're kind of close. And this is actually another kind of thing to keep in mind. Well, they're not super close, actually. If you look at this theta 5, right, it's, oh no, sorry, that's theta 4. Theta 4 is close to theta 4, and theta 5 is close to theta 5. So yeah, so they're pretty close, and actually that's something that happens when you use many of these optimization algorithms, is depending on where you initialize, you end up converging to kind of the nearest point that's sufficiently fits your data. And so many of these algorithms are not global optimization algorithms in some ways. They just do some local search with some exploration. So they do a little bit of exploration, especially in the line search part. But in general, they are quite local algorithms in the sense that they just try to find the nearest local optima. That's an oversimplification, but you know, that's the general spirit of these algorithms. And so you see here that these optimal parameters were somewhat close to the initial parameters that we used. Good. Now let's try to change the initial parameters. So let's go from these values here to these values. I had to play around with these for a bit, but basically the idea is you can show that for some initial values your estimates will be very different. And so I just ran the fit function on this. And now what I'm doing here is I'm just displaying the thetas. So you can see that the sigma is still close to 0.1, which is a true value. But let's display these two estimates. So this here coef of fpm1 displays or prints the name tuple. So let's kind of pull it out. So this gives us the name tuple of estimates for the first fit. And then for coef of fpm2, it gives us the name tuple of parameters for the second fit. When I do dot theta, this will give us only the theta value as a vector. And so here I'm just concatenating the two vectors side by side. And you can see that the estimates are wildly different for some of these parameters. Not just for the two parameters where we suspected some identifiability issues, theta 2 and theta 4, but even for some other parameters where there seems to be some multiple modes as well involved here. So there are multiple kind of local minima or local optima where you could converge to any one of them depending on where you start your optimization. And again, this is an issue that happens quite often with these pharmacometrics models because these models are far from convex when you're optimizing them. So convex problems have this property where if you start from anywhere, you always converge to the same solution. Well, strictly convex problems. But these problems that we have here are not strictly convex or even convex at all, and therefore they don't adhere to this property. And so you could potentially initialize it from different points and get different estimates at the end. Okay. Another demonstration that I wanted to show was what happens if I just increase the sigma level. So I use the same parameter values for simulation. I use the same seed for the random number generator. So I'm actually generating the exact same sequence of random numbers with the exception that the noise now is kind of amplified a little bit. So before it was 10% noise, now it's 20% noise. And so just by amplifying the noise a bit, we get a new subject, obviously. So let's do that. And if I try to fit this, so here I'm actually fitting the original population or the original subject from the true parameters. So these are the parameters that actually generated the data. So let's do that. Let's do this fit, which we did it before actually. And then next I'm fitting the new subject that we just simulated with the additional noise, also initializing it from the true parameters. So let's also do that. And now I'm just displaying them side by side again. And as you see again, there is quite a bit of fluctuation here, right? So that's quite a lot of fluctuation for the fact that we have a lot of samples, a lot of data points for this subject. And so you'll see that again, like even for simple things like changing the noise level could potentially give you some large differences in the maximum likelihood estimates, even when initializing from the same point initially, right? And so in general, this high sensitivity of the optimization to where you initialize is a sign of poor identifiability issues in your model. Now, it's not necessarily a strict sign, or it's not like a proof of poor identifiability. For that, you would need to do the checks that we did earlier. But you'll see that hopefully you appreciate that when you see things like that in practice, maybe your mind should now also consider the possibility that maybe your model is not really fully identifiable, or it could have either global identifiability issues where multiple parameter values, all of which explain the data, and they're very far from each other, or they're not close to each other, the parameter values, or it could be that within the vicinity of one set of values you have a whole like, arbitrary set of changes you can make, like you can make a whole lot of changes locally to the parameter values without really changing your prediction of the model significantly, and so you're still able to explain the data well while making local changes to the parameters. So that's the local non-identifiability issue that we showed before. Okay, so hopefully with this, you are at least somewhat convinced that just naively using naive pooled, but really any maximum likelihood estimation method is actually dangerous sometimes, in that if you actually draw conclusions based on this, these parameter estimates are somewhat different. They're significantly different, actually, in some cases. And if you're interested in doing any kind of hypothesis test or conclusions based on that, those are some significant discrepancies that you need to be aware of. And even the same thing earlier, right? Those are pretty significant differences that we should be aware of. And so I'm not going to convince you or to try to show you how to fix this in maximum likelihood estimation. And there may be attempts, there may be ways to actually try to overcome this a little bit, but like using prior distributions and whatnot to kind of try to work around the problem of poor identifiability in some ways. But actually the better solution, I would argue, and I think many would also argue that, is to really not just use point estimates at all. Is to use something called Bayesian inference. And again, I'm sure most of you are familiar with what that is, and so I'm going to assume that you know the basic concepts of it. But the main idea is that you don't really have to just get 1 point for the parameters that explain the data, but you could get a whole posterior distribution or samples from that posterior distribution, because for an arbitrary model, the posterior could be very complicated, like it has an odd shape for the PDF, and so you can't really represent it in closed form, but you can sample from it still. So when we get samples from the posterior, we can kind of get a good idea actually of how much uncertainty we have in some of these parameters, and it's a more rigorous way to quantify uncertainty than to try to, for example, play the standard error game with poorly identifiable models, where, for example, if you do bootstrap, right, you would a lot of the times with bootstrap you would initialize your optimization from the same point, which is the maximum likelihood estimate. When you reshuffle the data and then refit, that introduces some bias in some ways, because your optimization algorithm is always kind of going to prefer converging to some parameter values close by to the initial value than further away, even if both of them equally explain the data. And so you would, like all these methods basically are somewhat flawed. Once you have poor identification in your model, you end up violating many of the assumptions of the standard error estimation methods. Now, sampling importance resampling is in theory supposed to work. It's because it's actually Bayesian under the hood, but it is quite sensitive. So as a Bayesian algorithm, it's not necessarily your best choice, let's say, because it's quite sensitive to the choice of a proposal and so on. And so what I would suggest is, if you suspect you have some identifiability issues, is to use Bayesian inference, if nothing else, then at least for diagnosing identifiability issues. You could actually, given a lot of data, if you fit the posterior and you still get a lot of like variance in your posterior, even though you have lots of data, that's already kind of a pretty good sign, I would say, or indication of poor identifiability. So you could use Bayesian inference even as a diagnostic, not necessarily for the final result, but why not also for the final result? So the main difference in Pumas, if you want to actually do Bayesian inference, notice that this is the new model here. So this is the Bayesian model. We didn't really change that much except this param block. And what we did here was we defined something called the prior distribution, and I'm sure again most of you are familiar with that. But basically what this is, it's like a distribution version of a domain. So before we had the domain of each parameter. So maybe I can go back to that. So previously we had the domain of each parameter. So this is a lower bounded by 0, and this is a vector domain of length 5, etc. This doesn't really tell you which parameters are more likely to occur than which other parameters. So maybe the value 1 is much more likely than the value 10 million, right? But that domain doesn't really restrict that in any sort of way. But with a distribution, you can actually express your preference to some values over others. And you can still make it sufficiently kind of widely dispersed that it's not completely, like, it's not an overconfident prior. So overconfident priors are generally somewhat looked down upon unless you have a very good reason to use such confident or strong priors, as they're often called. So here, this is a relatively weak prior. It just gets the ballpark. So I use kind of the values somewhat close to the true parameter values, but not exactly the same. And it's a multivariate log normal distribution here with a standard deviation in log scale of 1, which again is like giving you some good margin to basically change the prior as you observe data. Now for the sigma, this is a proportional error model, so I also gave it a somewhat weak prior that says it's a uniform, like it's a uniform prior. It's a uniform prior from 0 to 1. This says basically any value from 0 to 1 is equally likely. Anything more than 1 is impossible, which you could argue is maybe a restriction. But think about it: if you have more than 100% standard deviation kind of in your model or in your data, then that's probably a very bad model that you have there, right? So it's like you're not doing much better than just predicting 0 the whole time. So this is actually not a very strong prior if you think about what this means. Now, if this were additive error model, that would depend on the scale of the observation, but this is not an additive error model. This is a proportional error model we're using here. So from 0 to 100% seemed reasonable. And we know the true value is 0.1, so we're not really pinpointing the true value, but we are roughly in the ballpark, basically. Okay, so again, we haven't really made any other changes. We just did this, use the multivariate log normal with the log, the means of the logs. So this is the mean in the log scale, and this is the standard deviation or the covariance matrix in the log scale. I here actually just stands for the identity matrix. So if I do I of 5, that's just the identity matrix of size 5. Yeah, it's nice, a nice kind of efficient representation of that using a diagonal matrix of booleans. So it's really efficient in memory. But that's just again a nice and somewhat loose prior distribution that we're using here. So we can go ahead and define this model. Now, next, to use Bayesian inference, instead of using naive pooled or FOCE or Laplace, in Pumas you would just define an algorithm called Bayes MCMC. And under the hood, this actually uses the no-U-turn sampler algorithm, which is kind of the gold standard for models where you only have continuous parameters, which is most of the models that we deal with. And so here I'm just choosing to sample 3,000 samples per chain. The first 1,500 samples will be used for adaptation, so that's 1,500 out of 3,000, per chain. And then we have 4 of these chains, and I'm choosing to parallelize across threads, and I'm using a random number generator for reproducibility and fixing the seed. And then I just call the fit function again with the same 4 arguments: model, data, parameter values or initial parameter values, and the algorithm, the Bayesian algorithm. Now running it takes about a minute, so I'm not going to rerun it here. But basically you can see the results here, and maybe it's better to switch to this version of the tutorial. So you can see the results here, and you can see that basically for the parameters where we suspected some kind of identifiability issues, we do get quite a bit of dispersion, right? So there's a lot of the standard deviation relative to the mean is quite significant, given that we have quite a few points, like 61 points samples in this one subject. And so you'll see that, again, we do have quite a bit of standard deviation here. Now the diagnostics look decent, so the R hat here, which is a useful diagnostic, should be close to 1. It's pretty good. The ESS, effective sample size, bulk, again, not bad. So many of these diagnostics are looking good, I would say. Now, just to be sure, what we do normally, it's recommended in general, is to discard the first 1,500 samples, which we use for burn-in, or which were used for adaptation of the algorithm. So during those steps, the algorithm, the sampling algorithm itself, the Markov chain Monte Carlo MCMC algorithm, is adapting its own hyperparameters while it's sampling. So it's doing this auto-tuning of its own parameters. And so to be safe, usually it's recommended, at least in the initial parts of this adaptation, to get rid of those samples and treat them as burn-in, essentially, which is just a term that people use in MCMC to refer to samples that we don't really want to count as part of our posterior samples. And so we're using the Pumas.discard function on the output of fit here, and we are specifying how many samples per chain to throw away from the beginning, and so that's here 1,500, and so we end up with a kind of subsample of the full sample here. Okay, so again, pretty straightforward so far. There's nothing surprising, but I guess the interesting thing is, again, the second and the fourth parameters where we suspected we had the most fuzziness in the model, or non-identifiability or poor identifiability, are also kind of demonstrated here, where we have a large standard deviation in the posterior distribution. Okay, just for rigor's sake, it's always recommended to look at the diagnostics to make sure that your MCMC actually converged, because like these numbers could sometimes be misleading. I mean, the R hat is a pretty good diagnostic usually, but sometimes it's also good to look at the plots just to see that everything is nice and mixed well together. So mixed is again another technical term people use in this field in MCMC to refer to the kind of behavior that we see right here, which is we have 4 different chains in 4 different colors, but they all seem to nicely overlap with each other, right? They all seem to kind of visit the same parameter values that all the other chains visit. So an example where chains are not mixed is if one chain is up here, another chain is down there, and they're not really visiting each other that much. And so well-mixed chains are basically what we see here, where these chains here are nicely mixed. You can also see that so MCMC ideally is trying to mimic random sampling, and so when you see randomness or something that looks like randomness like this, that's pretty good. That's a good sign. That's exactly what we're trying to achieve. And you'll see that, again, all these chains go up and down in what looks like or appears to be random sampling, which is the desired behavior in this case. Now, what we see is the values are mostly fixed, like the distribution doesn't change as you change this, like in the first, let's say, 500 samples, then second 500 samples, and so on. You'll see that roughly the distribution doesn't change that much, and that's, again, another evidence towards convergence. In general, you cannot really prove convergence, I would say. In MCMC, you can only kind of detect signs of lack of convergence, but you can also have signs of convergence, where you can have more and more confidence as you get more and more evidence or signs that the chains appear to have converged, or at least we cannot prove that they did not converge. And so here it appears that way. It appears that all these chains distribution doesn't really change a lot with the sample. Now, every once in a while, you see some jumps. You see these going up and down, kind of these spikes, basically, that we see here. And this could be indicative of perhaps another mode of the posterior that has a very small mass. So there could be a very small mass, probability mass, to some values up here, basically for some of these parameters. And that's what's causing this. But again, it is consistent. You do get these spikes consistently every once in a while. So it's not really something that happens only in one part of the sampling, but doesn't happen in another part of the sampling. It's somewhat consistent, which is a good sign. So consistency, noise, or randomness, or what appears to be randomness, and mixing. Those are all three things that we need to look for, basically, in this so-called trace plot. So that's the trace plot. Again, we passed with the output of fit or discard. So actually the output of discard is the same type as the output of fit. So these two objects here have the same type, and so you can pass them to the same functions downstream for diagnostics and plotting and stuff like that. Okay, next we have the autocorrelation plots. So these are, again, other useful diagnostic plots that I did mention. The goal of MCMC is to try to mimic random sampling as much as possible, but MCMC is not purely random algorithm. It's not actually doing random sampling only. It is doing something that can introduce autocorrelation in your samples, and so the previous sample can sometimes be a good predictor of the next sample, which is not the case if you have pure random sampling. And so the idea here is to kind of look at this autocorrelation over how many samples ahead we kind of are estimating. So the gap or the lag parameter, basically, between the samples. So how let's say how predictive of sample 3 is sample 1. So can sample 1 be used to predict sample 3? Can sample 2 be used to predict sample 4? Can sample 3 be used to predict sample 5? And so on. And so this correlation between two samples that are offset by a lag is what we're looking at here. And you can kind of adjust the parameters of this autocore plot to get like slightly different plots. But basically what we're seeing here is a function of the autocorrelation, the average autocorrelation over the lag parameters. So as we increase the lag, obviously we expect, so as we increase the distance between the two samples that we're measuring autocorrelation or correlation between, we expect that there will be less and less and less autocorrelation, right? And some people call this that the MCMC algorithm forgot where it started from. So in some ways, the sample 10 samples down the road is almost independent of the current sample, which is a good thing. That's a proof or an evidence that suggests that yes, indeed, we are doing something that mimics random sampling, at least over a wider lag. Now, a good MCMC sample or sample set shows kind of an immediate drop of autocorrelation with very small lags, so that maybe within a lag of 2, 3, 4, you see almost zero autocorrelation or zero correlation between the samples. Now, in this parameter, for example, it does persist quite a bit, so you'll see that maybe around the 5 or 6 lag point here, that's when we see a good drop of autocorrelation. But here, for example, you see that the drop is much more immediate. And so it'd be nice to have, in general, it's recommended, or it's a desirable property to see this sudden drop or immediate drop with a very small lag value. But again, this is not really a measure of or a sign of lack of convergence. You could have autocorrelation in your samples and your chains could have still converged. So this is not really a bad sign per se, but often it is. So it's not guaranteed to be a bad sign. But sometimes if you have extremely large autocorrelation, so the curve doesn't even go down that much, this could be a sign of lack of convergence as well. So it'd be nice to understand why, if you have this behavior here where the autocorrelation never seems to go down to zero, then why is that the case? So understanding that is important. But if it goes down to zero, but perhaps a little bit slowly, that's not necessarily a bad sign or a sign of lack of convergence. And we'll see again that all of the chains behave roughly in a similar way, so that the chains are somewhat consistent in that sense, at least consistent with each other. But if you really want to have a kind of faster drop, you can actually enforce it by doing something called thinning. So thinning, what it does is it basically takes like maybe every third sample or every fourth sample. So it subsamples your sample. It takes a smaller subset of your samples by doing maybe every or taking every 2 samples or every 3 samples instead of taking all of them. And so you can actually specify the ratio that you want to keep, and it will pick kind of the subsample that's that ratio. So in this case, it's 20% of your samples, and it will try to spread them across so that you have basically more lag between each sample and the next one. And so the idea here is that when we do that, obviously we see that the autocorrelation drops immediately, because now a lag of 1 is equivalent to basically a lag of 5 previously, where we because we took only every fifth step, or perhaps a lag of 4 actually in this case. So we took every 5th sample, and so it gave us a significant drop in this case. Okay. So in general, though, thinning is a bit controversial. So some people would argue against thinning because you are throwing away samples. And even though those samples are not perfectly uncorrelated, there is some correlation. So they're not equivalent. If I have 1,000 samples and they're correlated, they're not equivalent to 1,000 independent samples in terms of the amount of information they have. But they still have more information than if I threw half of them away. So if I took only 500 of the 1,000, even if they're less correlated, but those 500 as a whole sample, they have less information than the 1,000 correlated samples that we picked them from. And so in general, subsampling reduces the amount of information, and so it's generally not recommended to do that unless you have really high autocorrelation and you have a good reason to do this thinning, in which case you can again use the discard function. And notice I give it again the output of fit here. I specified the burden again, so it first removes the first 1,500 samples, and then from the remaining 1,500 it picks only 20% of those. So that's the idea here. Okay, so with that, that's basically all you need to know. There are a few more diagnostics, and I encourage you to look at our documentation, which has a lot of information on all the plots and all the diagnostics that you need to know about and that you can perform in Pumas. But that's kind of a glimpse of what you can do. So let's say that we're sufficiently convinced. We think that the samples look good, the chains are well mixed, and all the diagnostics are basically there's nothing to question there. They look decent. So now what? So we have the samples from the posterior. What is so special about that? What can we actually do with those samples? And the answer is, well, quite a few things. But first, let's walk you through, for example, how to sample from the posterior. So if I want to, like one thing you can do is try to sample from the posterior, like pick a sample from the posterior, use it to simulate. So I can simulate from the posterior distribution of, or the distribution of the response given the posterior distribution of the parameters. And the way we do this in Pumas is by passing the output of fit or discard to simobs. So simobs is our simulation function, which we've used before in a different setting. But basically about passing the output of fit with MCMC to simobs, and then specifying how many samples we want. And then you can say whether or not you want to simulate the residual error, so whether or not you want to get the predictions at the end, or you want to get the simulate the residual error as well. So you can specify that with this keyword argument, and then which observation times you want. And by default, this will just be the sample times in your subjects, but you can also change them. So you can simulate much more dense samples than your data to get smooth curves and stuff like that. So simulating is usually done for plotting and so on. but also for other purposes, of course. So once we have the simulation, so once we simulate like this, we can actually do a VPC. We can do a visual predictive check. So what is a visual predictive check? I'm sure everyone here is familiar, but the idea is to compare the distribution of your data to the distribution of some synthetic data or simulated data. And so in this case, we have the simulated data coming from the posterior. Well, we pick samples from the posterior, use it to simulate responses, and then we have 1,000 subjects as a result of this. And we have our original subject, which is just a single subject in this case. And so the question is, what can we do, or how can we compare those two? And so in this case, you'll see that so what we do in Pumas, we do quantile regression. So you can almost look at the quantiles here are basically just fitting the noise in the data, right? Because we have the standard deviation. We only have one subject data here. So actually plot the observations, and you'll see that the data quantiles are just kind of doing fitting the quantiles of this single subject model. Or single subjects data, but what's more important is the quantiles of the simulations, which is the blue part, the upper blue band here is the upper quantile kind of interval or prediction interval, if you want to call it, and then we have the gray band is the simulated median, and then the lower band is the simulated lower quantile. And so we'll see that again that the black lines fall naturally or fall nicely into the respective intervals, which means that there doesn't appear to be a mismatch between the distribution of the data and the distribution of your simulations. Now, normally with a VPC, you would do it with many more subjects. So this is not a very standard looking VPC, but you get the idea. The syntax doesn't change if we have more subjects, basically. So yeah. So that's one thing you can do. You can compare again the data, the observations that you have with your posterior distribution, and see that yes, so here perhaps you can just look directly at the black points, which are all the observations. You'll see them that they fall nicely within the posterior simulated values. So. And again, notice this is just a single line of code. It's customizable. You have a ton of options there that you can customize. If you have multiple observations, you can specify which observation you want to plot in this VPC while reusing the same simulations. And so a key aspect here is that we simulate once and then we can do multiple plots and VPCs out of these simulations here. So that's a nice way to kind of not have to repeat the simulation every time you do a VPC. First simulate, and then you can do the VPC as a secondary step, or perhaps multiple secondary steps for different types of VPCs. Okay, so VPC is good to look at to verify the fact that, or to verify whether or not the model is actually predicting our data well, or kind of modeling our data well. How close is the distribution of true observations to the distribution of simulated observations, and that's usually a good thing to check and double check. But what else can we do with the posterior distribution? So having kind of estimated this uncertainty in your parameters, we could potentially use this uncertainty in various scenarios. So let's say you're trying to optimize a dose for a patient where you only observed maybe the baseline covariates and the baseline values for the observations, or maybe just very few observations. Then you could use Bayesian inference to basically, given those observations, get an idea of all the possible parameter values that could have fit, or that could fit this patient's observations, or that can explain this patient's observations. And so by getting the posterior distribution, what we can do is then, given all or each of those samples, we can make a prediction, and then we can actually estimate probabilities of events. So one event, for example, is how likely, or what is the event of achieving a certain therapeutic range. So maybe an event of achieving a certain efficacy criteria, or avoiding a certain safety risk, or achieving a safety criteria. And so avoiding toxicity, increasing the probability of efficacy, those are things that we can actually do once we have these samples from the posterior, and we can propagate the uncertainty forward to predictions, and then use those predictions to kind of estimate certain probabilities of good events we want to happen and bad events we want to avoid for optimization purposes. And then we can tweak the parameters that we can control, like the dose level and dosing regimen and so on, in order to achieve a higher probability of success in treatment. So here I go through the value of uncertainty quantification a bit, and in general it's important to distinguish between two types of uncertainty that we can kind of see in this context. One that is basically due to structural identifiability issues, and then one that is due to practical identifiability issues. So in general, any uncertainty due to structural non-identifiability will not have an effect on the model's predictions. And so if I try to propagate the uncertainty forward, and the uncertainty largely comes from structural identifiability issues, which is mostly what's happening in this case, then I should not expect to see a lot of changes in the predictions. And so in that sense, using the posterior does not help that much. If all you care about is predictions, in that case, using the posterior can help. It can make your predictions more robust to bad fits and to bad estimates and maximum likelihood estimation. But the interval, the uncertainty in the prediction is going to be relatively small. And so doing good maximum likelihood estimation, finding the best parameter estimates could potentially perform almost as good in this case. The main power, though, of uncertainty quantification is in two different scenarios. So first, if you're actually interested in the parameter itself. So you want to get what is the probability that clearance is more than a certain value? What is the probability that a drug treatment effect is more than 0? What is the probability that a drug effect is drug A is better than drug B? So you're actually interested in the parameters, not just in the predictions, but the parameters have meaning, and you want to answer questions about the probability of this parameter being satisfying a certain criteria. In that case, having proper uncertainty quantification is necessary to answer these questions. And so even if, again, those different parameter values may not have an effect on the prediction because of structural identifiability issues in your model, but it's still good to know, or it's still necessary to estimate probabilities when it comes to your parameters themselves, which, again, maximum likelihood estimation methods cannot really provide these kinds of probabilities for you. So the other scenario, so that's one scenario where uncertainty quantification or Bayesian inference would be very useful. The other scenario is if you have insufficient data in your models. If your identifiability mostly comes from, or could be a mix of both. So it could be a mix of structural non-identifiability, but also there's insufficient data. In that case, the component of uncertainty that comes from insufficient data, basically, that will have an impact on the model's predictions. And so in that case, it's possible that maybe I only did early observations of the patient. I only did observations for 1 day. And so I don't have that many observations yet. And that means I can, there are multiple different models, all of which fit the first day or can explain the first day of observations, but perhaps they have very different predictions of what could happen the second day, or the third day, or the fourth day. And so in that case, because we have this limited data, even if your model is identifiable, we don't necessarily know what's going to happen in the future, because we only observed or very few data points, basically. So we cannot guarantee that only this parameter value is the true parameter value. We have some uncertainty in what parameter values are the true parameter values in this case. And so uncertainty due to insufficient data or practical identifiability issues, which is kind of a similar story. So even if your model is actually identifiable, but you just have insufficient data or you don't have enough data, then this uncertainty, those parameter values which are different in the posterior will have different predictions at the end. And it's good to in that case, it's good to know what all the possible predictions are that are made according to the posterior distribution, whereas maximum likelihood would kind of give you a single prediction from the point estimate. So, yeah. So that would be the second scenario. And again, the idea is to make your decisions more robust to parameter uncertainty. And in general, it's hard to actually know which of those two cases you're in. Is it the structural non-identifiability case, or is it the insufficient data case? And often it's a mix of both, or it can be a mix of both. And so that's why, even though conceptually it's good to keep in mind the difference between them, in practice it's really hard to actually tell what is the source of your uncertainty in your model. And doing Bayesian can just basically fix your problems in general, or make your predictions more robust to parameter uncertainty, whether this uncertainty came from structural issues in your model, or whether it came from practical identifiability issues or insufficient data in your model. So uncertainty quantification is a very important thing to do. And again, that's why, for example, people estimate standard errors and other stuff in regular maximum likelihood estimation, right? But in this case, we get it naturally from the posterior, and that's actually a good also point to mention, which is that Bayesian inference is somewhat analogical, or it tries to do the same thing as, let's say, a bootstrap. Perhaps it's based on probability theory, and it makes less assumptions about your model than Bootstrap does and about your data, but it is basically a conceptual replacement, if you like, for things like Bootstrap, and that means that when you run them, so often the runtime of fitting Bayesian models is one of its main kind of disadvantages, in that it can take quite some time to fit these models. So in this case, it took us about, I believe it was a minute, less than a minute, 33 seconds to fit this model here. But yeah, if you remember from the maximum likelihood estimation, it took much less time, and so we see here it took almost no time at all. And so the speed difference is often a disadvantage. Basically, the runtime speed difference is often a disadvantage of Bayesian methods. However, you think of a bootstrap. So when you do a bootstrap, you also have to wait often for a long time. You have to do many fits. And so a posterior distribution or a Bayesian fit basically gives you the same kind of information, perhaps better information about the uncertainty than bootstrap. And so when you're comparing the runtime, you should really compare the runtime of Bayesian inference to something like Bootstrap, and that will give you a more fair comparison for the kind of information you're getting out of the Bayesian fit. Okay, so again, let's kind of recap here. So we do have a few things we can do with these posterior distributions. We have the ability to propagate the uncertainty forward to get predictions, so that we can hopefully make decisions based on those predictions, like dose selection and stuff like that. We could ask probabilistic questions given our data. So what is the probability the drug A is efficacious, or that drug A has an effect compared to the control drug? And we can do all sorts of kind of what-if analysis or counterfactual simulations by changing some settings and then re-simulating. So we can do the simulation exercise, whether it's simulation or prediction exercise that we did earlier. And in some ways, this is just another example of this. We're propagating the uncertainty forward, but not just for the experimental conditions that we have, but for conditions that were never used in the experiments. And this could be used, for example, with optimizing doses, trying different dosing regimens, and so on. And then once we have that, we can still ask probabilistic questions given our simulations. So what is the probability that the AUC is more than a certain value, or the Cmax is less than a certain value? And we're going to see some examples here. So to show an example, here is an example where we can estimate the probability that clearance is more than 35. So clearance here is just the first parameter, theta, and the way we do this is using this, again, do syntax that we explained earlier. And here the do syntax does something slightly different. It's basically for every sample evaluating this block here. So P is the name tuple of parameters. So it's a name tuple in this case of theta and sigma. And I can access the theta field here, and then I can access the first number of the theta field. and then I evaluate this Boolean expression here of whether this theta1 is more than 35. So this will be true if it's true, and false if it's false, or it's going to be counted as 1 if it's true and counted as 0 if it's false. And basically what we're doing here is just take the mean value of that, which is an estimate of this probability, or the probability of this event here, the event that clearance is more than 35. So that's how you can basically get probability estimates of your parameters. Now I can do, for example, what is the probability that p theta1 or p dot theta1 minus p dot theta2 is more than 0. So I can get things like if this is the effect, like I can get like the difference in effects if I want to, or what is the probability that the difference in effects is more than 0. So you can do all sorts of arbitrary kind of complex queries here of your parameters to get probability estimates of various events. Okay, next what we want to do is evaluate the probability not the probability of some event in the parameter space. So that's an event in the parameter space, right? The clearance more than a certain value. What we want to do next is actually get or estimate the probability of some events in the prediction space, where we propagate the uncertainty forward first. So we do that with simobs again here, but in this case I want the predictions. I don't want the simulated observations at the end, so I don't want the noise at the end. So I just switch off simulate error here. And I get basically what people sometimes call the iPreds. But in this case, we have multiple of them, even though we have one subject. So we have a whole distribution of iPreds in some ways for this subject here. And it's only a single subject, so all of them are going to be corresponding to that one subject. Now, next, I can use something called the post-process function on the output of simobs. So this is a general function in Pumas that you can use on the output of simobs. Even in regular kind of non-Bayesian workflows. And the idea is to get some information, or to be able to define or evaluate some function of your simulation. And so the syntax for this, let's try to break it down a bit. So here we have, again, the same do block syntax. But in this case, instead of just having one variable here, we have two. So normally we just have like one variable p or some parameter values that we were looping over. But here we have two different variables. Gen is basically stands for generated. So this is all the generated quantities in your model. So you could access all of your various intermediate values in your model in the form of a name tuple. So this is the name tuple where I can access the dv field, for example. So the dv field would be the predicted value of dv, or the generated value of dv. And then I have the observation. So this is the observed value. And the reason we have both here is, even though we might just be interested in generated, but sometimes you want to, for example, get what is the probability that my prediction is more than my observation. And so normally we'd expect this to be around 0.5. If your distribution of predictions and distribution of observations are roughly matched, you would expect that half of the time your prediction is above your observation and half of the time it's the other way around. And some people call that the Bayesian p-value sometimes. So you could do these kind of comparisons. And again, these are both name tuples. So this is the name tuple, and this is the name tuple of the observations, and this is the name tuple of all of the generated quantities in your model. In this case, we're only interested in the dv field. And so what we're doing is we're just loading this NCA package and evaluating the AUC and the Cmax given those predicted concentrations. And then we get the value here. So that's going to be a scalar for each scenario, basically, for each simulation. That's a scalar. And then I'm building a name tuple out of those two scalars. And so the end result is a vector of length 1000, because we had 1000 samples. And for each of those, for each element in this vector, we have a name tuple that gives us both the pk AUC and the pk Cmax values here for the various scenarios that we have. So you'll see, again, there is some discrepancy, but perhaps not that much. And this can be actually attributed to the fact that the most of the uncertainty in this case seems to stem from structural identifiability issues in your model. And so the output doesn't have that much dispersion, or the prediction, the posterior predictive distribution does not have too much standard deviation. The standard deviation is somewhat low or small. But you see still that there are some differences here, right? So we're able to simulate the various AUC values and Cmax values from the model. Now, once we have that, we can use a similar syntax to the one we used before to query the probability of clearance being more than a certain value by using the same mean do function here, or mean do syntax, where we pass to the mean function the output of post-process here. And we estimate the probability in this case that the AUC is more than 90 and Cmax is less than 15. So these are arbitrary criteria that you can select. But basically it gives you how many of these scenarios satisfied this criteria. And this is your estimate of that probability. Now you can do it separately. I can get the probability the AUC is more than 90 and the probability that Cmax is less than 15 separately here, and then just display them side by side. And yeah, so that's just an example, right? You can do all sorts of things. You can define your own kind of function that you can actually use here as well, and then estimate the probability of that function being more than or less than a certain value. So you could really do arbitrary Julia code here, which I think is very empowering in some ways. Okay, so next, what I want to show is counterfactual analysis and dose optimization. So what if I want to try a different dose? So this is a subject that we have. We tried the data that we observed was given a certain dose, but maybe I want to see what's the other, like what if I gave the other dose instead of the dose that I actually gave? What if I gave a different dose? What would the simulations look like? Or maybe you want to change the future part of a dose. So you have a dosing regimen. You gave the first part of it, and then you observe the patient, and now you want to change the future dose of that subject and observe, maybe optimize the future dose of that subject or the future part of the dosing regimen of that subject that have not yet been administered and observed. And so in that case, what we do in Pumas is essentially define a new subject to represent this counterfactual scenario, this new scenario that we want to test. In this case, the only difference between this new skeleton subject, so it's another skeleton subject with no observations here, but the only difference between this and the true or the original skeleton subject was the dose, or is the dose. Instead of 3,000, we're giving a dose of 3,200. And that's the main difference. But again, you could get creative with the kind of changes that you make here, so that you could really define any dosing regimen that you want here and try to optimize that, or multiple such dosing regimens. You could use different doses and so on. Or maybe different drugs even and stuff like that. So you could really define anything that you want in your subject. You could even define different covariates. So if this subject here doesn't have any like baseline or time varying covariates, but if it did, you could also change that as part of your counterfactual analysis when defining this new skeleton subject. Now next, what we're going to do is simulate from the posterior predictive distribution. So here I'm simulating from I used the thinned samples in this case, and I could have used just the unthinned version as well. And I'm simulating about 1,000 scenarios from that for this new skeleton subject, or the new scenario that we have, or the counterfactual scenario. And again, I don't want to get the residual error at the end, so I switch that off. And we do something here which is specify the index of the subject. And this is mostly relevant when we have population models, when we have multiple subjects and random effects. Because when we're simulating, often we're interested in using the posterior samples from the population parameters, but also using the posterior samples from the individual parameters, the random effects, basically. And so when you specify subject 1, it will basically use the posterior samples of the first subject. So it assumes that this subject here is a counterfactual scenario, or is doing a what-if analysis on the first subject, which means that we're using the samples, the parameter values that were fitted to the first subject's data. That includes, again, those individual parameters, or the random effects. So if you want to simulate from the posterior of the random effects of a specific subject, you use the subject's index here. If you don't use a subject index here, it will treat this as a new subject. And what that means is it's like it's going to reuse the samples or the posterior samples from the population parameters or for the population parameters, but it will sample from the prior distribution of the random effects. So that's an important distinction, that when we say subject equals 1 here, if your model actually has random effects, you would be sampling from the posterior of the random effects, whereas if you don't specify subject equals something in this SimOps call, you would be sampling from the prior distribution of the population, the random effects, and still sampling from the posterior of the population parameters. But in this case, we don't have random effects, but I wanted to show this just to be more general. So in this case, both cases are equivalent because there's actually no random effects in the model. It's a single subject model. So that's how you would simulate, again, for this counterfactual scenario that we have. And then once we have those counterfactual IPREDs or counterfactual simulations without residual noise, we can do the same thing, get the AUC and the Cmax using the post-process function here. The only difference is this input to the post-process. Then we can estimate the same probabilities. And we'll see that the probability increased. When we increase the dose, we increase the probability of achieving this arbitrary therapeutic criteria that we set. And we can actually break it down again and see why. So the second probability actually didn't change, it's still 1, but the first probability changed a lot. Compare this to the original probabilities here. Right. So we can use this to play games and see what dosing or different dosing regimens result in, and hopefully choose one dose based on certain criteria that we specify, therapeutic criteria that we specify. Okay, so a final kind of demonstration here is just stressing on the point that if you have structural identifiability issues, your predictions will not have a whole lot of uncertainty in them, even if your parameter values have uncertainty, assuming you have a lot of data in your case. So if you have dense sampling and you still have a lot of uncertainty in the parameters, that's usually a sign that you have structural issues in your model and not just insufficient data problem. And so here I'm just demonstrating that I'm getting the average value of the IPREDs. So I'm using this other syntax here where I can pass the output of SimOps. So this is the output of SimOps here, and I'm passing it to the mean function and doing this again, do syntax here. And in this case, I just get the mean prediction. So this is the average prediction that I'm interested in. So this will give me the average prediction across the 1,000 samples. And then this will give me the standard deviation of the prediction across the 1,000 samples. Now, each of those is going to be a vector of over time. So mu will be a vector over time, and sigma, or mu's and sigmas, will be a vector over time each. And so what I do here is I ignore the first time point, and I just divide the rest. So I divide the sigmas by the mu's. I want to get the relative standard deviation here, ignoring the first point because the first point has a mu of 0, basically. And so ignoring the first points, you'll see that the relative standard deviation is actually very small. It's like 2.5%. So it's the predictions are not very sensitive, even though, as we saw earlier, there was a fair amount of uncertainty in the parameters themselves in the posterior. But you see that doesn't translate to a whole lot of uncertainty in the predictions. And so this hopefully demonstrates that this model likely had some structural identifiability issues. And this could itself be used as another diagnostic, right? If you don't want to do this whole Fisher information matrix eigenvalue thing, you could already use this as a metric, like see how much change happens in the prediction for the change in the parameters. But arguably, you should probably just do the Fisher information matrix because it's cheaper and it gives you a measure of sensitivity that you can use to diagnose identifiability issues. But both kind of tell a similar story here. So to conclude, these are a whole bunch of references that are useful to look at. They're mostly in the optimal design space and the identifiability analysis space or part of the literature. And I hope that with this tutorial, you've been sufficiently exposed to enough material to help you first identify or test for identifiability in your model. But not just that, but even if you decide to use your potentially poorly identifiable model to hopefully select the better algorithm, essentially, for this kind of model. And so hopefully this helps. And as part of this tutorial, we also demonstrated a few key aspects of a workflow when using Bayesian inference. You don't just usually fit your model and that's it. You need to do something with those results and answer certain questions. And so hopefully I helped you get an idea of how you can do that in Pumas with very few lines of code. Thank you.